Yeah, Professor. So shall I share my screen? Yeah, I can share it. Oh, like you need to enable it, Professor. Yeah. Um, so can you see the screen? Okay. Okay. So shall I start the presentation? Yeah. So good evening, everyone. Oh yeah, yeah, I can on it. Yeah. Okay. So, good evening, everyone. Today, I'll be describing the basics and advanced formulation for determining the factor of safety using finite element approach with some examples and case history for better understanding. So, I'll be presenting only one case history due to time constraint. Other case history will be produced in the report. Um, like, yeah. The factor of safety plays a major role in every geotechnical design, and its definition varies from problem to problem. When analyzing a foundation, we can define factor of safety as the resisting capacity of the foundation to the applied load. Whereas in the case of slope stability, it is defined as the ratio of shear resistance offered by the soil against the driving force along the failure plane. So it varies depending on the problem that is under consideration. So if we take factor of safety equal to 1, that means the structure supports the exact stress that it was subjected to. So as we increase the load, the structure tends to fail. So the definition follows for the factor safety equals to 2, where the structure will fail at 2 times working stress. Many methodologies that are followed to determine the factor of safety. So we have the conventional limit equilibrium method, which includes the following analytical formulations shown here, like the Kalman's method, method of slices, Bishop methods, and other conventional formulations. Um, as we have advanced or complicated problems in the real life situation, it becomes cumbersome to extract results using limit equilibrium method. So this is where the numerical modeling came into scene, which uses the concept of stress reduction method to solve the boundary value problems. There are many methods like finite difference method, finite element method, the boundary element method, meshless method, and finite volume method. In this term paper, I'll be concentrating on the finite element method. Uh, like it is a computational technique used to obtain solutions of boundary value problems using shear strength reduction technique. This technique enables the finite element modeling to calculate the factor of safety by gradually reducing the cohesion and the angle of internal friction, that is the shear strength parameters of the soil until the failure occurs. So the formulation of the finite element involves the following process. So a real life complex body object is scaled into simplified physical modeling in which the material property and the boundary conditions are assigned to simulate the field condition. The simplified object is further discretized into several elements system or element connected together by nodes. Then each element is considered separately to form element equation, which considers all the external and internal stresses of the system. These elemental equations are combined together to form global equation, which is then solved using to find the unknown variables using several methods that is explained in the further slides. Further, the stresses and strains corresponding to the nodal displacements are obtained, thereby determining the factor of safety of the model's slope or any geotechnical problem. The field or element is considered to be the domain of interest, in which the unknown variable are represented in the form of differential equations. Initially, let us assume a 2D case where a single field variable phi of x comma y is determined at every point such that the governing equation will satisfy the variables at variables similarly at every point of the body. The point means the node of the finite element. And as an example, for a three-noded triangle, the field variable is defined as phi of x comma y, which is a function of n and phi, where phi is the field variable at each nodes and n are the interpolation functions, or it is also called as shape functions or bleeding functions. So these are in the form of polynomials with independent variables. These are derived to satisfy certain field conditions at the nodes. Like you want to find the displacement of the node, it corresponds to the stiffness of the nodes. The primary characteristic of FEM are given in terms of element stiffness matrix, which contains geometric and material behavior of the soil under consideration. Let us consider a linear elastic spring as shown in the figure to understand the formulation of finite element method. The linear spring can only support axial loading and it's directly affect the deformation of the spring. The force per unit length or the force per unit deflection gives you the stiffness of the spring, which is the proportionality constant between the force and the deflection. Assuming that both the nodal displacement are zero, we get the relative spring deformation as delta is equal to the deflection at spring 2 minus the deflection at spring 1. Considering equilibrium of forces, the nodes at the nodes, we get the applied nodal forces as F1 is equal to minus K into U2 minus U1 and F2 is equal to K into U2 minus U1. So these stiffness are obtained based on the free body diagram of this the spring under consideration. So the above equation could be derived in the form of matrix as shown below. Uh, the F vector represents the nodal force as the action. The U vector represents the displacement of the nodes as the behavior of the sample, and the property of the spring are embedded inside the stiffness matrix. The values of K, U, and F varies depending on the problem under consideration. For elastic problems, the K value is the stiffness, for the behavior U is the displacement, and the action F is the force under consideration. It varies depending on the problem under consideration. So now let us consider a system of two springs and try to solve the and try to form the global equation of this two spring system. The equation of spring in matrix form is given by the first two equations, which is determined based on the free body diagram of the individual spring under consideration. By applying the compatibility condition like u1 of 1 is equal to u1, like the displacement at first node is equal to the displacement of the spring 1. Same way, displacement of the second point due to the deflection of spring 1 is equal to u2. So these conditions are applied to the above matrix, and we get the last two equations of the spring. Now, combining the equations considering 3 degree of freedom, we get the final stiffness equation as given in the third equation, where the forces F21 and F22 are combined together, which is equal to the applied force F2. Applied force F2 at the spring 2, at the node 2. Once the displacement is determined, we could calculate the strain in the body by comparing the deformations with the original dimension of the body, thereby determining the stresses at every nodal points. Hence, the FOS is calculated by dividing the stress at failure by the initial stress found in the soil. So the above formulations are just for 3 degree of freedom system. For real life problems with huge number of nodal junctions, will result in complicated finite element formulations, which initially involves formulation of element level equations as given below. When these elements are isoparametric, The shape function only depends on the natural coordinates like the coordinates s and t, which are derived using the equation given below, which includes the Jacobian matrix. uh, the Jacobian matrix are the function of the interpolation functions. By inverting the above equation or finding the inverse of the above equation, the global derivative of the shape function could be determined. Uh, After determining the global derivative of the shape function, the next step involves formulation of global equations by accumulating every elemental equations in the given form. The global stiffness matrix is obtained by accumulating the individual elemental contribution after considering the common degrees of freedom. So, hence, the final obtained global stiffness matrix contains elements after neglecting the elements which are similar due to symmetry and singularity of the stiffness matrix. Then we apply the load and displacement restrictions to the fully defined boundary value problem that has to be analyzed. Once the global stiffness matrix has been established, it has to be reduced into smaller system of simultaneous equations, which are easier to be handled. For this, we take into account the symmetry of the matrix by considering the diagonal and upper triangular elements of the global stiffness matrix. Further, after determining the bandwidth of the matrix, we decompose the stiffness matrix in the form as shown in below, as shown here, where L is the lower triangular matrix and DM is the diagonal matrix. The final form of the equation looks like this. So the whole stiffness term is divided into the lower triangular matrix and the diagonal matrix, respectively. Having determined these final equations like the triangular factors, the diagonal matrix and the lower triangular matrix, it is then solved as a stepwise process as shown below by following forward and backward substitution methods. The final step involved only the displacement vector obtained from the backward substitution in determining the true displacement vector of the soil body. When the soil body is assumed to be behaving linearly elastic, the stiffness matrix contains the terms which are governed only by the material's Young's modulus and the Poisson's ratio as shown below. So, with these formulations on the side, we now move on to understand the importance of mesh refinement using a case study performed in Backus finite element software. This analysis considers a simplified version of a slope at a coal handling plant at India, whose dimensions are given below. The material is assumed to follow Moore-Coulomb failure criterion and assumed to be homogeneous and isotropic. Four different mesh sizes are used to study the dependency of element discretization in varying the resulting factor of safety of the soil body. So the value of zero point 0.4 produces a finer mesh when compared to a value of zero point 0.8. So we are varying the mesh size and checking how the competency of the factor of safety for different mesh size are. The results for the above conditions are given below. The factor of safety value becomes more conservative when the mesh size is finer than a coarser one. We can see the deformation contours of four different analyses under consideration. For the first analysis, the factor of safety was revealed as 1.404. And for the second one, with the mesh size of zero point 0.8, for the same mesh size, the factor of safety is reduced. Also, the analysis was carried out by installing a soil nail and checking the efficiency of the soil nail installation and increasing the factor of safety of the slope. For the case of 10-meter long nail, it was not long enough to connect the slipping wedge to the remaining body of the soil sample. Therefore, it did not improve the deformation considerably. When the slope did not have any reinforcement, the obtained factor of safety was around 1.4. In the second case, a 15-meter long nail was used. This nail resulted in significant higher factor of safety of 1.58, which was 12.86 percentage increase comparing to the case of unreinforced slope. As we keep on increasing the soil nail, the difference in the factor of safety was not influenced that much because of the wedge, the slope wedge being controlled within the 15-meter length nail. So the outcomes of the case study was obtaining the factor of safety of the soil slope by finite element analysis is an effective method for slope failure investigation when compared to any other limit state equilibrium method, which are cumbersome in nature. Finer mesh refinement could lead to more conservative predictions of the factor of safety. Unlike traditional methods like limited equilibrium methods, finite element method does not require any arbitrary partitioning of the critical surface selection, which are selected prior to the calculations. So this is today's presentation. Thank you, Professor. Oh, yeah, Professor. Just I presented only one case study due to the time constraint. It's like, yeah, yeah. Okay, yeah, yeah. Sharing, yeah, yeah. Okay, yeah, yeah. Until the failure occurs, until the soil body collapse. Yeah. Like uh, the multiple soil layered soil properties are also considered to form the stiffness matrix, so that it considers the cumulative, the approximate value of the layers and find the solution. It considers a uniform homogeneous layer with approximate values of the material properties. I think so. Yeah. Okay. Yeah. Yeah. Okay. It depends on the thickness of the layers and its contribution to the failure. Okay. We are reducing. Yeah, we are reducing the tangent of the friction angle. Yeah. Yeah. Okay. Conclusion. Yeah. Uh, mention. Okay. Okay. Yeah. So can I stop sharing or? Yes. Yeah.
Excuse me, so the answer was we reduce all the layers by the same amount? What was the answer?
we'll like we'll find the tangent of the like we'll approximate it based on the layer contribution. Okay. Will it not be conservative? Will not be too conservative, Professor? Okay, 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 okay.
Yes, Professor Akshay here. I don't know my other partner is in the in the course or not. So I'm only going to present my presentation. Okay, so can I share my screen now, Professor? Okay, thank you. So can you able to see the screen, Professor? Yeah. Okay. So here I'm going to present about the analysis of earth rotating structure by using the two different method. First is the finite element method and the other approach is the finite difference approach. So we all know that before these two methods are invented, we have some conventional methods such like a Rankine earth pressure theory and the other is a Coulomb theory. So Rankine theory and the Coulomb theory both have some own shortages. So when we try to solve any example based on the Rankine theory, so we need to just go with some assumptions of that. So we always assume that the horizontal soil layer, the and there is a no friction between the soil and the retaining structures, and the the structure should be the retaining the structure that retain the soil should be a vertical only. So if it is tilt or it have some slope, that it can't be work over there. And the other thing is the water table is not considered in that. So there is any no space for the gamma saturated or gamma w. And other thing is the Coulomb theory. So now we going about for finite element method. So first, the finite element method is itself the name is suggests that we just decide some like element from our complex element, and we just do a mathematical computation to find the factor of safety to find the displacement and the strain stresses and everything in that. So we can also find based on that like a deflection and the bending moment in each and everything. But in the finite element, we have to go with the stiffness matrix. So it is a key part of that method. In the finite difference method, when we have a very big or any kind of the complex equation. So we divided it in a finite, in a some small finite part, and we do a derivation of that. So we need to think that the first, the both the spectacle domain, spatial domain, and the other is the time domain are discretized, and the broken we can broken into the number of steps, so it can reduce the complexity of that equation to solve, and we can easily find the value by using some algebraic formulas. So based on that we can find everything, and in a finite difference method, so we can go with the ordinary difference equation, and other is a partial difference equation. Sometimes the equations are not collinear, so we are converted into the linearic form, so we can easily solve that, because the linear it should be a linear to solve use this to apply these methods. So in the finite element method, we just we just mostly dividing the compacted object into simple form and manageable elements. So it is sometimes replaced by the model which is consisting the finite number of the discrete element, which is fully continuously over there. And the nodes, then finding the nodes are a very important in that. So here we also, to go with that, we have to understand one thing first in that, we just make we in that we make a two type of the matrix. First is a exact stiffness metric, where the like elements is easily identified, just example as a truss or anything. Another we make some approximate stiffness metric, where we need to like select any kind of the element. So element we can select by the like internal stabilized earth structure. Like if it is internal stabilized structure, then we have like a anchor or any kind of the like soil retaining key or anything. So based on that we can select the structure, but the selection of that structure that mostly depend on the some few things, so we have to understand that. So based on that we can easily select any kind of the element. So first is a geometry, so we have to understand the geometry of with that structure, I mean for a returning structure. Then also then expected physical behavior, so how it behave when we like going with the like surcharge loading, or when we don't have that surcharge loading or anything, that time we have to just estimate the physical behavior of that, and and also it is important that the degree of accuracy, when if we need the more accurate result in some kind of the region, so that time we just divide the elements in a number of terms, so it's maybe automatically leads the more degree of accuracy, and the time and the functions that are available for that. So in that we mostly select our like a safe function and all here. So for the finite element method for analysis of the specially returning structure, so we need to just follow, we need to establish these points. So when we have these are the key elements points, then we can derive a stiffness matrix, and then we can find our unknowns and the and in solution. First we go with to find with the establishing the finite elements mass, then we can also identify the primary unknowns, and we also derive the safe function, which is based on the 1D 2D or a number of nodes we are selected in that. And there is the derivation of the stiffness matrix is a very important part in that. And the like constitutive soil model, like we have to also derive that, and we can easily solve that primary unknowns and like secondary unknowns. Based on that result we can interpret the final result of the our structure. So here I'm just showing that for establishing the fe mass, so it's totally depend upon the number it's totally depend of the number of element which are choose for the for solution of that, and what kind of the physical problem we are facing in the particular soil structure. And we can also select based on the required accuracy, like a 2D 1D 3D, we can also go with that. In the second thing, then identity of the primary unknowns. So it is a very necessary that first of all we have to know what we need to find in that. Like our agenda to find the deformation or the shear force, so we need to select that as our primary unknowns. So we can easily go by that. And derivation of the shape function. Here I am just showing the one example of that this is the one kind of the thin bar. And so we all know that there is a two kind of the reactions on the both the ends. So one is displacement and one is the reaction, the u1 u2, and theta1 theta2 is our rotation. So based on that, so we can write our stiffness matrix. So stiffness matrix also depend like this matrix is also sometimes depend upon the elements like of the anchor elements, or we choose like our beam or the whole retaining wall. So based on that, the first is this is very much important to define the stiffness matrix. So to interface the element to design in a sheet pile or retaining structure. See, we mostly like insert the sheet pile in the mostly earth retaining structure. So based on that, we also understand that there is a like a huge difference between the stiffness or of the soil and the returning structure, and the between that the inserted sheet pile. So we have to be the very careful that time. So because there is a huge difference in the soil and the pile stiffness. So based on that, we can decide our stiffness matrix. But most of the like in the most common use, we mostly use the four nodes at the intersection surface. And there is also the thing we have to define that constitutive soil model. So there is also a theory behind that to find that the soil model. It's also noted by the she the constitutive soil model is one of the vital part in the settling up the numerical solution. It describes the simple relation between the stress and strain. There are also things that we have to know. In the numerical problems, some numerical models are some are linear elastic model or some non-linear elastic model, elastoplastic model, Mohr column model, hardening model. So we have so many models in that, but we mostly go with the linear model. So we like go with the linear elastic model or Mohr column math models. So here the and the other is a linear elastic model. Here we can easily see that it's showing the relationship between the stress and strain when we have a like isotopic material in that, and our Young modulus and Poisson ratios are also in defined that like this way. We can easily say that here it's a low hook law we use that the stress is proportional to strain, and then we use introduce the C in that. So so we can write by this way. Now, the most other important thing is to define the boundary condition, because the to derivation of the equation we need to know what is the boundary condition. To most of the boundary condition when we are solving the especially geotechnical problems, we need to decide the boundary condition. The boundary condition is sometimes defined as like based on the which kind of the mesh we are established for the solving these problems. And there are all assumptions that sometimes we assume that the symmetry and the plane stress relation also we say, assume in that. So sometimes also important to see that there is like any kind of the relation between or any interface between the soil and that structures. The mesh boundary, I already said that this mesh boundary will be selected based on the which kind of the size we have selected for the mesh. And also we can find the mesh boundary location based on the doing the trial and error methods. So for the solution of that returning structures, so we are just need to complete this all the steps. So in that we can easily solve by like primary unknowns, then secondary unknowns, then we can easily do interpretation of that. So this is the method we mostly go for finding the some any kind of the load structure or designing of the retaining wall by the FEM. So the accuracy is also important in the finite element, and if we need to create it more accurate, then we need to give the more data inputs. So we can go with that. Now I am just turning to the finite difference method, the finite difference approach. It is also important, the finite difference approach. The word is itself suggests that we have a, like there is an equation in that, so we can easily do the like differentiation of that parts, and we can go with the by we can do like discretize some spatial and the time interval part in that. and we can decide based on that the shape function of that, and we can proceed for that. So first of all, to solve this kind of the equations or problem, in especially in a Rankines or theory, so we mostly select we develop the equation first for the bending moment or shear force in a one state variable. So then we just develop the grid points. So based on that, mostly we just introduce the 1 meter interval. In the next example, I just take a 1 meter interval in that, and it is the most reliable to choose the 1 meter, so we can easily calculate the grid points in that. And we can also develop the different equation by expected schemes which is used in that. And we can also after that solve the different equation, and we can easily find the bending moment shear force by using the forward method. And we can also use some numerical methods in that, and we can also go find the deflection in that too. So now for that, first is to solve this. I already told that the Rankines work when we have assumed some like some kind of the parameters in that. First is the cohesion is in that the numerical. So we assume that the cohesion is negligible, and the water level is not considered in that, and the surcharge load is not is given in that. See, we have two loads in that. First is the dry sand on the right hand side and the left hand side. So there is a soil is presented in that. So I here for just showing the process, I just take some numerical values over there, like angle of internal friction I took 35, cohesion 0, surcharge load is 0, density of the soil we just take 17 kilonewton per meter cube, and the height of the retaining structure up to that the edge point, so it's like up to 2.5. So the boundary condition in that, so very important, they play a very vital play in that. So we assume then that at the top of that, we assume there is like a bending and bending moment and the shear force at the like top of the embedded retaining wall, it is zero mostly in that. So when we try to draw our any kind when we try to write based on that our driving moment and the shear force equation, so we can like plot pressure variation diagram over there, and based on then I just wrote here, I just written here all the moments in that, uh, based on that all uh, distance interval. So here we can easily say, we can easily find all the things just by making the proper uh, equation for that. So we can also derive we can also find the bending moment and shear force just by using the spreadsheet too. So here I am just showing that, so here by showing that there is a variation with the depth, bending moment and the shear force. So I'm just showing over that how it is varied from that. So we can also calculate the deflection using the FDM that. So here we gonna use the formula. This was invented by the one researcher or scientist, the Fabian Kim. So it's showing that it can be used to find the deflection along the earth retaining structure, which is embedded sheet pile earth retaining structure. There is a basic relationship between that. The bending moment easily we can find by the EI W square upon dz square, and also we can find the shear force by the d is equal to EI d cube upon d cube W upon dzw. So here we take just 1 meter weight, and we derive in the simplification in the other form. So EI is equal to d raised to 4 upon dz square plus CW is equal to Q. This is the standard equation by the way, by derived by the uh, the scientist the Fabian cube. So in that we know, so the coefficient of the W is the wall deflection in that, and the C is the coefficient of the soil reactions or earth reaction. It also known as a soil reaction modulus. So it is very important because we consider it when we are solving any kind of a matrix. So C value must at least two non-zero elements we are defined for that, and we can find this value by the Gaussian elimination method, or we can also find this value of that by the PY graph of that scientist. So based on that, we can proceed that. So the final conclusion about this method are like we can use the FEM and FDM. These are both reduced like a complexity when we are facing in the conventional method. So it's like making the more easier task, but it should be a more accurate when you are when we are selecting the elements or any shape function or stiffness of that. So, so in kind there is some assumption that we only use for the when there is a soil vertical and all, but it's used when there is any kind of irregular shape of the backfill over there. And it also stimulates some stages of constructions in that. See, we mostly use the Flex and Plexus software to solve this example. Can also ultimately use the spreadsheet too. So thank you. So I mostly use that the finite element method. So because of that, we can easily we can easily just define some elements in that, and there is a simple key factor approach in that. So we can directly go with the stress strain relationship and all. So I just mostly use the FEM. But in FDM, when I choose the FDM, I just need to be a very accurate for selecting the stiffness and also the save function with the time variable. So I just mostly use the FEM for my solution.
Yeah. Good evening, all. Today I'd like to present a presentation on the constitutive relations for sensitive phase and the solution of related engineering problems. First, let us look at the overview for today. I'll introduce the topic, get some objectives for the presentation today. What is some of the soil constitutive models that have been used by the researcher, case study to back that, also the conclusion for the presentation today, and some references and acknowledgements at the end as well. Okay. First, let us ask ourselves what is sensitive clay? Sensitive clay is actually a type of soil that has a very high undisturbed shear strength and a very low impervious shear strength. Now, as you can see from the picture, the soil when it's intact, it can carry a lot of weight, but when you expose it to some disturbance or cyclic loading, you're going to see that the same soil flows like a liquid. As there is an example of a landslide in DC. What happens that that soil may be disturbed by earthquake is born in DC. So there, if you
Your
have
voice is
sensitive clay,
breaking.
sorry, can you hear me properly?
Yeah, now I can hear you. Yeah.
Okay. So what I was saying is, if you expose the soil to cyclic loading, the failure can be catastrophic, and it can be like the soil can flow like liquid, as you can see in the diagram here. Now, the property that you can describe this type of soil is sensitivity, as we'll learn more in the presentation ahead. Now, the next thing I want to talk about is particle finite element method. Now, this is a numerical modeling method, but it is specific that the researcher has used in the paper I've I've done. So basically what we are trying to understand is how is it different and why did they try to use this method. So you can define this method as being the mixed procedure that considers the meshless definition of a continuum represented by a cloud of particles, and then treats the assemblies of those particles with the standard mesh method, that is the standard finite element method using the mesh. As you can see in the diagram, we have the first stage there, cloud of particles. Those are basically what we've defined, we've specified to the model. Those are the, you've specified to the model at a time, certain time tn. Then you give it some boundaries. The second stage, provided it with define some boundaries in the domain, and then using the coupling the Delaunay triangulation of these particles with the alpha shaped method, we're trying to give them those triangular nodules and to create the mesh. Now, subsequently, the discretization of the continuum is performed with the finite element mesh, MN, as you can see, and the corresponding Lagrangian equations of the motion are solved. Now, the steps here are usually followed by each, let's say at every iteration, we basically have the 3 steps here. As you can see, Cn+1 is the next round of the iteration. However, the solutions actually are updated from the previous cloud. That means the particles are usually with updated information in the next cloud. However, the reason for using this method and not any other method is because of, in this method, you can actually update those particles. I mean, you can either separate, you can remove the particle from the model, or you can add the particle to the model. That is using, because you can use tolerance. If the solution is getting separated, like let's say it's going away from the other parts, like really far away, that means you're separating the particles long way from a certain distance that you don't want. Or the solution is the particles are going together, a lot of them are together, like nucleated in the domain, and you don't want that to happen. So in between the model, you can actually add or remove from the model. So that is one of the aspects that the researchers wanted to work with, or get the versatility of the model through here. Now, let us just stick together and look at the objectives for the presentation today. It will be to break down constitutive models, and then to present an example of the models to integrate to solve an engineering problem. Now we have first of all, I'll just go through the soil constitutive model, and then I'll present the example, and then we'll try to make the things work together. So the soil constitutive models, we have a classical one, the MCC, modified Kamkle method model. This model actually has been modified over the years as scientists or researchers have evolved and used their knowledge to bring up new variations of the model so as to solve different types of problem in geotechnical engineering. So we've had the Sunny Clay, we have the Sunny Clay 1, S Clay 2. So different models are there out there to use in respective for respective solutions that you want. So the researchers in this case have used S-Clay 2, which is the isotropic destructing method. That means, which we are going to learn ahead why I'm talking about the destruction and constructing of the particles and all that. So this constitutive model here is used to yield, it's used for the yield and plastic potential function. That means they want to calculate the plastic potential of the soil when it's affected by, let's say, a load of a certain value. So in here we have the formula is right there. Some of the variables, S is stress minus the P prime I. P prime is the effective mean effective stress. We have the critical stress ratio from the triaxial compression. PC is the internal hardening parameter. And then we also have alpha, which is the kinematic hardening parameter of the model. Next is the soil structure effects. So this is now regarding the soil structure, whether the bonding and then the debonding, or let's say the destruction of the bond. Right here, the PC again is the internal hardening parameter. The chi here, chi is used as a bonding amount of bonding, and it is provided like it's a constant. We have the ST, as I've shown you, it's sensitivity, is to use to calculate the sensitivity of a soil. And PI is just a variable used to create the relationship here. Now the change in PI, which is calculated using the V is the defined volume. Then we have the lambda I, which is the gradient intrinsic normal compression line, which is found from the E-log curve that I'll show you later. The delta epsilon PV, that one is actually, which is the plastic volumetric increment. Now that is very important to understand, as we'll see further. So this is the soil destructuring model. So the previous one was to construct it together. This one is now to destructure it in the model. So these are basically constitutive models, and they'll be merged together later on to create the whole from a numerical model. So in here we have the shear again. However, on top of the volumetric plastic strain, we now have the deviatoric plastic strain, which means to remove. So the function of the change in shear, which is the bonding, is actually a function of the plastic deviatoric strain and the volumetric plastic strain. The A and B are constants. Those will be provided in the solution. So basically, these constitutive models were merged, integrated together using a commercial software Abacus by the researchers, and the accuracy of this was the integration process was done because of the ability of the Abacus software to merge them together and allow the researchers to do some versatile calculation using it and look for different solutions from the constitutive models, like they want to look at the pore pressure changes, plastic strains. They want to look at the resistance of the forces. So now I'm going to actually introduce to you, this one is the last constitutive model is for just the kinematic hardening, and this is the step. This is to explain to you like how you can play with the step function. Like the step function here, we have the volumetric plastic strain is equal to the volumetric. If the volumetric plastic strain is greater than 0, then we'll have the mean. So if you see the angular brackets, that's for the mean value of the volumetric plastic strain. And the other way around, if that is 0, that means the volumetric plastic strain is less than 0, which will eradicate one of the value here. That means it can be used to solve. And delta alpha is actually the kinematic hardening cofactor. And you can see below that the X alpha controls the relative contribution from volumetric and deviatoric plastic strains. So again, we are talking about here bondage and destruction of the particles. Now, let us look at the case study now. What will happen is put on the shorelines. It's dug into the soil right there where we have sensitive clay. Now, in the case study, the pipeline is placed halfway into the soil. That means 0.5 D if the D is the diameter of the pipe. So if it is put inside 0.5 D, the surcharge, as you can see in the diagram, it's 200 kPa. We have some defined boundaries for that. The net was created using 0.25 D near the pipeline. You can see the mesh is really thick. It's really small in like value, and as it expands higher. Now, the main reason for the researchers to use this numerical modeling method and to verify their result with another researcher who's already done this research but not using this versatile method was just because of the way that sensitive clay is, because of its plastic behavior, like because of its
You see that when it's intact, it's intact, it's very strong. However, if there is cyclic loading from the water, from ships, from something, if the pipe gets cyclic loading, what happens to the soil beneath it? It will be disturbed and it will start flowing like liquid. However, there's another case of consolidation. If the soil consolidates, then you have a scenario where the soil is gaining strength, but it's reducing in volume, but it's gaining strength after all. What is that strength after it's gone through consolidation? So all these are questions that the researchers can get answers from using such a model by doing simulations. Now, the second graph here shows the resistance is on the horizontal axis with the depth of the piping. So as I told you, the pipe went down 0.5 D. So you can see here that if you look at the results of a non-sensitive clay with the sensitive clay, you can see that the non-sensitive clay actually, as you go deep, the resistance increases. However, for the sensitive clay, as you go deeper, the resistance reduces. That is because of the weaker, that is because of the disturbance I told you, the sensitive nature of the soil. Because its remolded strength is very low. As soon as you disturb it, it's going to not going to give you any resistance, as you can see from this diagram. Now when the simulations were done, and you could see that this is another beautiful aspect of doing the numerical modeling, that they were able to get contour plots of plastic strain. Now the first formula we saw, that the plastic strain at embedment depth. So the graph A is for sensitivity of 10, a sensitivity of 2. So sensitivity of 10 means the soil is more sensitive. That means it's more erratic with the behavior. And then the C is non-sensitive. Now you can see in the non-sensitive, when the plastic strain is actually uniform. I mean, it's uniform, very nice shapes and all that. However, if you look at the more sensitive and the less sensitive, now this here shows the soft behavior of the soil, the softening. We have the softening and then we have the hardening, right? So this is really soft because you can see in the sensitivity of 10, we really have a deep circular failure, slip surface. The slip surface is really deep in the sensitivity of 10. It's actually trying to fail in a progressive manner. You can see progressive failures because of polygons starting to crack away. However, in the less sensitive soil, you can see that there is some impact, but however, the slip surface is actually more shallow than the one in the sensitive. So the more sensitive the soil, you'll see that the failure will be much deeper and you'll have a larger slip surface, and probably a very, in case if this was like a slope, it will be devastating because the landslide is very much vulnerable in that condition. Now, this is a second result that they obtained is using about the soil structure. Now, I told you that X is a bonding factor of it. Now, if you see here, the bonding in when the sensitivity is 10 is actually reducing really, the bonding is reducing. You can see the blue color shows less bonding and the red color shows more bonding, if you can understand. So you can see that in sensitivity of 10, there is a lot of blue there, and the blue is right deep inside near the slip surface and into the polygons as well. However, in the sensitivity of 2, you can see that the blue surface is just along the slip surface. However, it doesn't go that much deep with the 0.5 depth of the pipe we have. The third we are looking here is excess pore water pressure contour plots here. Now, again, it's between a non-sensitive, less kind of sensitive, and a very sensitive soil. Now here you can see again the non-sensitive is a gradual change in the pore water pressure, like it is gradual change, and as you can see the pore water pressure is actually changes positive. The pore water pressure change is positive. However, if you look at diagrams, compare diagram B and C here, you can see that the red spot is just at the embedment depth, like at the depth of the pipe, you can see the red dots in both A and B. However, in C, you can see that excess pore water pressure is actually starting to reduce. It's starting to reduce and going towards negative, as you can see. Much of more green, you can see much more green and yellow even at the base of the pipe there. So basically, to conclude the presentation, we were able to learn about the PFEM numerical method, which is used to explore the constitutive relation and its application in engineering problems. Several constitutive models are integrated to deliver various important properties of soil. The numerical model is able to provide numerous visual interpretation of the results that may be used to understand the soil characteristic in a much better way than classical soil mechanics. These were some of the references I used, and I'd like to thank Sabetamal 2021 for using the research work. Acknowledgements to Dr. Infante. Thank you for your attention.
Excuse me for the constitutive model. Did they use the associative flow rule or non-associated flow rule? I didn't understand it.
Sorry.
For the plastic strain, did they use associated flow rule or non-associated flow rule?
Here?
Yeah. No, in your constitutive.
Sorry.
Was the plastic strain normal to the surface of, or it was not normal?
Oh, okay. Unfortunately, what I'm still digging on in the working out of the formula, because this is for my term paper. What I've done is I'm actually doing research on what it's already available, and I'm working on the formula and trying to understand how they come up with the result that I have. So yeah, I may not be in a position to answer that question yet.
Okay, thank you.
Yeah.
No
Yeah. I will do the present first. Okay. Okay, hello everyone. Can I do it now? Hello, Professor. Okay. Hello everyone. I'm Shu and my partner is Kobe again. Today we will talk about the formulation of flow and the contaminated transport in saturated soil. Sorry. I will focus more on the flow, and my partner will focus more on the contaminant transport. Let's start from the flow. We all know that the freshwater resource have not been able to meet human needs well, and human activities such as the industrial waste discharge have led to groundwater contamination by chemical pollutants, which has increased the shortage of freshwater resource. To reduce contaminants, there are three basic process of contaminants are mainly involved because of the increasing concern about agriculture and other industrial contaminants migrating through the unsaturated zone and contaminating groundwater. It is critical to better understand the formulation of flow and contaminant transport in the unsaturated zone. Let's review the Darcy's law. Darcy's law describes the flow of a fluid in a saturated zone. Henry Darcy used experiment and found that the total flow rate is proportional to the head loss over a certain distance, and obtain this formula K is a constant representing the easy of flow of liquids through the medium. By recognizing the hydraulic conductivity is influenced by the amount of saturation. Darcy's law can be extended to unsaturated condition. This amount can be measured by the fraction moisture content theta, which are between 0 for fully dry and 1 for fully saturated. Thus, we get Darcy's law for unsaturated medium, where the function k theta is material dependent. In order to track how fluids move through a medium, we need to understand theta throughout time, and the result equation is called Richard's equation. First, we should know that hydraulic pressure head is equal to the capillary pressure head plus the elevation head. And then we can rewrite the Darcy's law. At the same time, we use the continuity relation to obtain the Richard's equation. This form of equation is known as the mixed form. Two additional forms are popular in the literature as well. One is the head-based. Another one is the saturation-based. Also, we can call it the theta-based. And third, we can describe both the mixed and the head-based version of Richard's equation using Euler scheme, and both forms use an average hydraulic conductivity. To develop a more robust approximation, we can use varying finite difference schemes to solve it. Here, I show you the derivation of one of these methods. In the head-based equation, because of the generally low-line reality of this system, solution must be solved in an iterative manner. And then we have the Picard iteration. This iteration is a relative simple method that serves as a good baseline for solving the implicit system. We donate the M iteration for a variable x as xi, and n is for the time, and m is for the iteration stage or the level. Finally, we can get a fully implicit screen solution as shown here. After that, we can the equation is organized as this form, which we are more familiar with, and combine with the equation for theta and k to solve the actual questions. in order to obtain more stable results, there are other methods to describe the Richards equation as shown in the table 1. However, Richards equation by different FT schemes solution that the mixed base form has better result than the head base form. In the table 2, it shows the A, B, D, and E coefficient for the mixed form. And the conclusion of the flow, here I'm not mentioned about the time limit. In fact, the equation remains unstable when we take too large unit time. For this equation, we can see that the Richards equation is already more complicated for 1D unsaturated zone flow, and there are more cases to consider when we push the 1D equation to a 3D. I finish my part, the rest will be finished by my partner.
Thank you, Shiyu. So I'll be taking over for her. So I'll be taking care of the contaminant part of this presentation. So just to quickly give a brief about contaminant transport. So there are a broad range of chemicals in the form of fertilizer and illegal dumping that seep through the soil layers. And this raises environmental concerns, especially when you consider their long-term effect on groundwater sources. So the unsaturated soil layer acts as a medium between the surface and these groundwater sources. So contaminant transport in this region, in the unsaturated zone, is studied and explored, is still being studied and explored, so we can better prevent and control the movement of harmful substances. And finite difference models are one of these techniques that are used to model and study the process. So taking you through the analytical solution. So over here, we have the equation of mass balance, where the first term denotes the rate of change of total concentration, and the second term denotes the rate of change of chemical mass flux density, and the last would be the change of mass per unit reaction of the sources. So now the total concentration includes the solid, liquid, and gaseous phase. And as for the flux density, for simplicity, we will be only looking into the liquid form, where we have the advection, dispersion, and diffusion processes. So we look more into the flux density, and over here for flux density of advection, this is the equation where Q is the volumetric flux density, C is the concentration of the solute in the liquid phase. For diffusion and dispersion, theta is the volumetric water content. This is the thing that governs the saturation of the soil. And over here, the constants DLH and DSL are the coefficient. So these are constant. These are dispersion and diffusion in soil water. And this is under the rate of conflux. When we assemble the equation together, the total flux density would be for the liquid phase, and we can combine constant. All this dispersion has higher effect with diffusion, and the transport equation in the liquid phase is shown as such. And moving on, from the mass balance, we find the advection dispersion equation, and again for simplicity, steady state flow, it leads to the advection equation. From the V is the average pore water velocity. And to implement the finite difference method, we would do a discretization in time and in space. The subscript J denotes the time, and I will be representing space. The only unknown variable where it is a forward difference in time and a central difference in space. So this equation depends on the concentration of the nodes in the previous concentration in the previous nodes. Now, the only drawback with this method is that if the boundary conditions are not constant, we would be having a lag. That means the the boundary condition would be looking back into the previous time level, which does not agree with physical laws. Now, to counter this, we would take it a step further as an explicit solution where the boundary conditions are considered in each level of the solution that we are looking for. And because of this, we are left with three unknowns, and they all can be solved by coupling them all the formulas for all the nodes, which will create a matrix. And this will be a tri-diagonal matrix as such. And for each constant, for each of these values, these are the definition. And this matrix can be solved using MATLAB to find the concentration in the next time level. So another scheme that we can use is a Crank-Nicholson scheme, and this one is much more stable and accurate compared to the previous two. And because the solution is found at time level j plus half, we would be seeing a second order difference in both time and space. Now, this is the weighted difference solution, weighted difference solution for the finite difference method, which is found from the advection dispersion equation. And over here, we have this value epsilon, which is a temporal weighing coefficient. So when epsilon is 0, it is a Crank-Nicholson time-centered scheme. I'm sorry, when it's epsilon 0, it is an explicit scheme. When epsilon is 0.5, it's a Crank-Nicholson time-centered scheme. And when it's 1, it's a fully implicit scheme. Now, the solution to the numerical scheme, it becomes more complex for transient problems. At this point, we would need estimates of water content and fluxes, and this can be done using the numerical solution of Richard equation, which my partner Shiyu had previously mentioned in the first half of the presentation. And these values are important to assemble a matrix and solve them. So while finite differences can be easily done for simplistic transport methods, one major disadvantage is that it would get complicated when we include 2 and 3 dimensions. Yeah, thank you for your time. And
You mean the theta? Uh,
it will be changing the average pour water velocity for the contaminant part. So yeah, it will change this value.
Because the theta changes and uh, we know that for the Darcy's law, the K is the consistent, but this time when the theta change and the hydraulic conductivity will be changed with the material. Okay, but when the theta changes, the hydraulic conductivity have changed and to influence. Actually, I have we have two model. Actually, when we to solve a real question, I have shown you that we have the theta is uh, a function of the head, and also the hydraulic conductivity is also about the head. So at the final, when we have to solve the question, we use the head to combine these two parts actually. And uh, uh, about the head and the hydraulic conductivity, we have the two model. I remember one you have teach us about the Benz model, the head changes and the comparative pressure changing and the uh, saturation change, and then our hydraulic conductivity will be changed. That's a relationship. I'm not showing here, but I have found some literature about that. Thank you.
Yes. Yeah. First, thank you all of your people for your presentations. Let me share my video. Okay. So my presentation is about analysis of slope stability using material point method. To begin with, slope stability analysis methods primarily focus on the slope's initial failure. However, the risk of failure depends on the post-failure behavior. For example, you can see different modes of failure here. As you can see, we can have large mass triggered by the slope failure, or a small amount of mass triggered by the slope failure. But when we have large mass, it poses a considerable risk to the buildings and people's live around this slope. Therefore, we need to model that. But how to model it? The first method that comes to our mind is FEM, finite element method. But for large deformations, FEM faces mesh distortions and it cannot return good results. There are some other methods such as discrete element method, which tries to model soil particles separately. It can model this kind of behaviors, but it is very, very computational demanding. There is another method which I am going to present to you called the material point method. And material point method is a hybrid Eulerian-Lagrangian approach that utilizes moving material points with computational nodes on a background mesh. So what is Eulerian-Lagrangian method? Mr. Euler and Mr. Lagrange here try to explain it to you. So if you want to analyze parameters of a flow, you can stay in a fixed point and investigate those parameters. This is a Eulerian view approach, and you can go with the flow and try to investigate these parameters. This is a Lagrangian view. So I want to give you a bird view over the NPM, then we can go to formulations and how to implement and find out how to implement it in the code. Uh, when we have individual particles, we need to turn it into a continuum assembly. And after that, we need to turn it into some elements. We need to discretize it into some elements. And in our method, we need to discretize it into some material points. Then we go through our computational cycles. First, we need to map material points information, as you can see on B1, to our grid nodes. Then we need to solve momentum equations on grid nodes. After that, we need to map information back uh, from grid nodes to our material points. After that, we need to solve constitutive law and update our material point information, find the new position of our material points. Now we have all of our information in our material points. Therefore, we do not need our information in our nodes. So now we can reset our mesh and go for our next step. It was a Lagrangian view because we traveled with our material points, but there is a view that called Eulerian view. As you can see, we have a background mesh which actually keeps still after each step. So this is a Eulerian view. So what are our governing equations for this method? We have conservation of mass, absolutely, but the conservation of mass is automatically met in most versions of NPM since each material point has a set solid mass and it won't change during our calculations. The core relationship in the NPM is conservation of momentum. And absolutely there is conservation of energy, which here we just use mechanical work as the sole source of energy, and we discard heat effects and other source of thermal energy. So how to implement it numerically? First, we need to turn our equations into weak form so that we can implement it numerically. If you consider this configuration here, this general configuration, we can write this equation to describe it using the virtual work. And by using integration by part for this term and using Gauss theorem after that, we can expand it to this form and use this form to describe our system. First step to solve this functional is to discretize it into some elements. We need a space discretization. For that, we need shape functions n and strain displacement functions p, which I think Akshish talked about that, Arvarant, I think. And then we need, then by substituting these shape functions and strain displacement functions into our previous functional, we can reach the general forms of F equals to MA. Don't think it's complex, it's so easy. And after that, we need a material point discretization. Oh, it was a bad heading. It is material point discretization. We need to discretize those elements from the previous step into some material points. And then we need to calculate our lumped mass, traction force, gravitational force, and internal force. It is the same as Gaussian integration points in FEM. Then we need time discretization. In here, we use explicit method as we had in our course. So now we want to implement it in the code. We need a computational cycle. We need an algorithm. The first step to do that is to create a lumped mass matrix by calculating the nodal mass using the shape functions. Then after that, we need to examine the internal and external forces, as you can see here. After that, having the mass and having the forces, we can easily calculate our nodal acceleration. Using our nodal acceleration and shape functions, we can update velocities at material points. And by up and now we can update the momentum. As you can, if you can remember, I thought that I talked about solving the momentum equation at the nodal points. Here we solve the momentum. We calculate the momentum at nodal points, and using that we reach the velocities at the nodal points. Having that velocity, we can easily calculate the nodal displacement, and after that we can calculate the strain increment. And now boom, that's our stress update. Using our constitutive model, we can update our stress. And we have only 3 more steps. First, we need to update the material points volume and mass density. Then we need to update the displacement and position of our material points. And now we have all the updated information in our material points. We don't need the values in our nodal points, and we can reset it and discard those values. Some researchers try to use this and try to use this method to model the initial failure and post-failure behavior. For example, Wang et al. And Wander et al. In 2016 and 2017 tried to do that. They successfully modeled this behavior using different angles of a slope and different, for example, infiltration. Here I tried to present the formulation for dry state, but you can add water, you can add saturation, unsaturated states to this formula. Thank you for your attention. If you have any kind of question, I would be happy to answer those. Yeah. Yes, yes. Because yes, yes, yes. As you can see here, our volume changes, and because our volume changes by the strain increment, we need to calculate a new volume in our next step, and our density will change in the next step. We need to calculate it. Uh, yeah, by a strain increment. We calculated the strain increment using the nodal displacement and nodal displacement from the momentum equation. And using that strain increment, we can the volumetric strain. Yeah, yeah. The yes, yes, explains it. I did. So I think we have different values x in different nodal displacement in x, y, and y directions, x, y, and z directions, and using that we have different strain in each directions. Using those three uh, strains, incremental strains, we can calculate our uh, volumetric strain. Yeah.
Hello, Professor. Uh, about the question you asked me, can I share my screen again so I can explain it well? Okay, I will share my screen again. Okay, can you see the paper? Okay, actually about the saturation, first we care about the capillary pressure, and we have the equation like this. We have the non-wetting fluid and the wetting fluid on the unsaturated zone. And then we have two model like this, two common relationship. We have these two to describe it. I think this one you have mentioned it before. And yeah, and then we have the Darcy's law. Here you can see the K theta, the hydraulic conductivity, which is equal to the Kr is the relative permeability turned between 0 and 1. And K is the constant we used for the Darcy's law on a saturated zone. And how can we get the Kr? Then we still use these two model to get them. This is the relationship to combine the moisture content and the hydraulic conductivity. Thank you. Okay.
Thank you, Professor. Professor, I want to ask you one thing. So right now we did with our presentation. So when we have a final solution of our term paper to you, like final submission. Okay, on like a 22nd December. Okay, thank you, Professor.
Excuse me, Professor. May I ask about the final exam? Uh, is there any software that we need to use? Is there any limit? Uh, so we do not need spreadsheets or okay. Right. And for the exam, okay, thank you.
Professor?
And okay.
Oh, the timings for the examination will be same, right? The timings for the examination, it's 7 to 10, right? Okay, the same. Okay. Okay, the question paper will be available in the Bright Space, and we need to download it and upload it, right? After writing. Yeah, okay, that's fine. Okay.
So about the exam is an open book exam or okay. Thank you. Thank you, Professor.
Thank you, Professor.
Thank you. Yeah, Professor.
Thank you. See you soon in person.
Thank you, Professor.
Yeah, yeah, that was the case of the course.
And now
We
we
will be
relax about the
contacting you
subject.
for any numerical method problems.
Bye bye. Have a good night.
Bye, Professor. Early Christmas. Happy Christmas.
Happy New Year, Happy Christmas, Professor, in advance. Thank you.